Hi everyone, this is a lecture video for class 14 of PH 125, and today we're going to be talking about the restoring force, also known as the spring force. We'll also be talking about tension, and we're going to start on centripetal force. Okay, so just a reminder, chapter 6 is all about common forces. So last time we talked a good amount about friction, which is the force between surfaces in contact. And remember, friction is the force that resists relative motion between those surfaces in contact. And then today we're going to talk about the restoring force, which is related to springs. We'll also be talking about tension, which is a force that's transmitted along a string or a rope. And then we'll also be talking about the centripetal force, which is any force pointing towards the center of a circle. Okay, so let's get started today with the restoring force. And so when we have a spring, the spring with no net forces acting on it is in what we call its equilibrium state. And so then the total length of the spring without any forces acting on it is what we call the equilibrium length. And so if you were to start at one end of the spring and measure over to the other end, we would set the end of the spring, one of the ends of the spring, you would just say that that's the equilibrium position. So that would be the position that we're going to call x equals 0 when we're working with springs. Okay, and so whenever the spring is in equilibrium, we have no applied forces on the spring, and the spring isn't exerting any forces either. Okay, so specifically in this class, we're always going to be working with ideal springs. Ideal springs are massless and they obey Hooke's law. So what is Hooke's law? It tells us that the force exerted by the spring is equal to minus kx. So k is just the spring constant. It's some positive proportionality constant between the force exerted by the spring and the displacement from equilibrium x. It has units of newtons per meter, and it depends on the individual's make of the spring. So we say that a spring that's really stiff, so one that's really hard to, you have to push really hard to get even a small change in the length of the spring, we would say that that's a stiff spring, and that would have a really high K. If it's really stretchy and you only have to apply a little bit of force to get some big amount of displacement, then we would say that this is like a really loose spring, or it would be less stiff. Okay, and so that occurs when it has a smaller K. All right, and so then the other thing in this equation, this Hooke's law equation, is the force of the spring. This is specifically the force exerted by the spring, and this is what's referred to as the restoring force. And it's not to be confused with the force that's applied to the spring. So normally there is going to be a force applied to the spring causing it to be displaced from equilibrium. And then specifically what Hooke's law is telling us is about the force exerted by the spring. And so that's going to be a Newton's third law pair with the force applied to the spring, right? So they'll have equal magnitudes and opposite directions. Okay, and then finally, x is the distance that the spring is stretched or compressed relative to its length at equilibrium. So at equilibrium, we define, one end of the spring to be at position x equals 0. And then, for example, if we compress the spring, then we would be, in this case, the spring would be going to the left, right? And so I would say my displacement from equilibrium is going to be negative. In that case, I would be applying a force that's also in the negative x direction. And then you can see the spring force would be going in the opposite direction, which would be the positive x direction. So this comes directly out of Hooke's law, right? Because Hooke's law, you can see, has this negative sign in it. And so in other words, whenever you push on the spring in one direction, so you move it away from equilibrium in one direction, the force exerted by the spring is trying to push it back into the opposite direction. In other words, back towards that equilibrium position. And I think this can get a little confusing in terms of, trying to figure out the signs and the math, but it's actually kind of intuitive if you just think about it. When you think about an actual spring, if you push down on it, you can feel the spring pushing back up on you, right? And if you stretch it, you can feel the spring pulling it back towards the center line. So whenever you get kind of bogged down in the signs, just take a moment and think about physically what is happening. What would you feel if you were doing, either the compressing or the stretching of the spring? And then just remember that you can define your signs. As long as you're consistent in your direction, you'll be okay. All right, but so in this specific example, and in general, we talk about compression being in the negative x direction, and then the spring force will be in the positive x direction. If instead you have a stretched spring, then you would be displacing it in the positive x direction relative to its equilibrium position. And so then the spring force would be pulling it back towards equilibrium. In other words, it's going to be in the negative x direction. Okay, and as I mentioned, then the applied force and the spring force are an action-reaction pair, and so they are going to have equal magnitudes and opposite directions. Okay, so let's do a quick example here. We have a 2.5 kilogram mass that's on top of a spring, and the spring has an equilibrium length of 4 centimeters. When the mass is placed on the spring, it's compressed by 0.9 centimeters. And we want to know what is the spring's spring constant. Okay, so how would I go about solving this problem? First thing I would want to do is think about what is, what are these values that I've been given in my problem statement. So what are the important values, right? So the important values, remember, are the displacement from equilibrium, x, and then also we're going to need to know the force exerted by the spring. Okay, so the displacement from equilibrium, x, you can see I've drawn in the x equals 0 line here. And so the spring is displaced from equilibrium to some new position. We would say x here is going to be minus 0.9 centimeters. Okay, so I'm defining the downward direction to be the negative x direction here. All right, and so then the force that's applied to the spring that's causing it to compress, that's just the force of gravity, right? So that's really going to be the force of the weight of the 2.5 kilogram mass sitting on top of the spring. So that's going to be force applied is just equal to mg, and specifically it's in the minus y hat direction. Okay, so that's our applied force, and so then I know that the spring force is in Newton's third law pair with that applied force. So that tells me that the force of the spring is going to be going upwards, right? The force of the spring is going to be equal to minus the force applied. So they have equal magnitudes and opposite directions. All right, so I'm pretty much ready to go with solving the problem here then. So I know two things about the spring force, right? So first of all, I know that the spring force is equal to minus kx. And here we know that x is that minus 0.9 centimeters. Okay, and then I also know that the force of the spring is equal to minus the applied force. In this case, because the applied force is downward, that means that the force of the spring is just going to be equal to mg, right? It's going to be positive mg. Okay, and so we know those values. The mass is 2.5 kilograms, and g is 9.8 meters per second squared. Okay, and so since these two things are equal to each other, I can just go ahead and solve then for k. So k is going to be equal to, my minus signs cancel here, so it ends up just being equal to the 2.5 kilograms times 9.8 meters per second squared divided by the 0.9 centimeters. Okay, and so when I plug that into my calculator, I got 27. And if you look at the units here, kilograms meters per second squared, that's a Newton. And then we have 0.9 centimeters in the denominator, so I end up with newtons divided by centimeters here. And so my answer is going to be B, 27 newtons per centimeter. Okay, so that pretty much wraps it up for the spring force for now. We're going to circle back to springs in a little bit when we talk about harmonic motion. This is still a few chapters away. So we're doing light springs for now. We're going to circle back. So we're going to move on then to strings and tension. So tension is really just a pulling force that's transmitted through something like a rope, a string, or some other like thin one-dimensional object, basically. And it's really an action-reaction force at each end of the string, and it pulls equally in opposite directions at every point along the string. So this is kind of crazy to think about, but if you look at the diagram over on the right-hand side, if I had picked any point along the string, I would know that the tension is pulling equally in opposite directions at every point. So it's going to be pulling up on the box, right? And it's going to be pulling down on the ceiling at each point along the string. In this course, we're specifically going to be working with ideal strings, and then also when we talk about tension, we talk a lot about pulleys. And so we're going to be talking about ideal strings and also ideal pulleys. Ideal strings are massless, just like our ideal springs were, and ideal pulleys are also massless, and another important thing about them is that they're frictionless. So of course, these are idealizations, but they're pretty good approximations in general. Okay. And so when we have ideal strings and also ideal pulleys, we can know two specific properties about the tension. So when we have ideal strings, what that tells us is that the tension is exactly the same at every point along the string. So in other words, the tension at any point along that one string is going to have the same magnitude. So if we look at this diagram over on the right-hand side, I have a few little tension arrows drawn in. And so I know that the tension pulling up on box 1 is going to be equal to the tension pulling up on box 2, because the tension everywhere throughout this entire string is going to be constant. It always has the same value everywhere on one single string. All right. And then we also know that we have an ideal pulley here in this bottom figure. And so whenever you have an ideal pulley, then you continue to have the fact that the tension has the same magnitude at everywhere along the string, but you can have a change in the direction of the tension. So that's why the tension on box 1 is pulling upwards, whereas the tension on box 2 is also pulling upwards, right? And so you can see, as I went over the pulley here, you can see the tension pulling on box 2, it went from pulling downwards over here on the left-hand side to pulling upwards over here on the right-hand side. And the same thing for the tension pulling on box 1. Right, so that's really the purpose of the pulley. It just changes the direction of the tension. But when you have an ideal pulley, it can't change the magnitude. So we still have the fact that the tension on box 2 is equal to the tension on box 1 in this case. Okay. All right, so let's do a quick conceptual question here. So in this top case, I have a 1 kilogram weight hanging from the ceiling, and I want to know what is the tension in the string. Okay, so to figure this out, we would think about drawing like a free body diagram. Here, the tension on the string is pulling up on the box, and we know that the weight contributes to a weight pulling downwards, right? And so then if I were to define downward to be the negative y direction, I would say the net force in the y direction is equal to weight downwards, so minus mg, plus tension upwards. This is also equal to mass times net acceleration in the y direction, but the box is just hanging there. It's not doing anything. And so that tells me that the net acceleration in the y direction is 0. So I can go ahead and say that the net force in the y direction also has to be equal to 0. Then I just rearranged and solved. T must be equal to mg, which in this case would just be 9.8 newtons. All right, so what about if instead we had the same 1 kilogram box, but now it's hanging from a string that has been suspended over a pulley? Now what do you think the tension in the string will be? Okay, so it turns out, remember we said that pulleys, they change the direction of the force, the tension, but they don't change the magnitude. So really this second situation here is identical to the first, except that this pulley changed the direction of the force, right? So you can think about the wall being kind of like the ceiling, right? So it's basically we've tilted things around the ceiling using this pulley. And so that immediately tells me that the tension in the string must just still be equal to 9.8 newtons, since all I did was hang my string over a pulley, which all it can do is change the direction. You can also draw a free body diagram and do the same sort of analysis that we did in case 1 if it wasn't obvious to you that all we have is the same situation, but hanging over a pulley just changes the direction of the tension. Okay, last case here, we now have 2 boxes hanging over 2 pulleys, and they are perfectly balanced. So in other words, they're in equilibrium, they're not moving. And now we want to know what is the tension in the string. Okay, so I think this is probably the trickiest case to think about, but the key here is that it's perfectly balanced. And so actually, there is no difference between the second case here and the third case in reality. The 1 kilogram mass acting on the left-hand side that replaced the wall, it's basically doing the exact same job as the wall. And so the tension in the string is going to be the same. And we can figure that out by just thinking about a free body diagram on mass 1. Since the box isn't moving, we know that the net force acting in the y direction on block 1 must be equal to 0. That net force is also equal to the sum of the forces acting on block 1. So that would be the weight of the block downwards minus m1g and the tension upwards. Okay, and so then we can just solve for t. We get m1g. Once again, that's going to be 9.8 newtons. Okay, and so that last example was a specific example of something that we call translational equilibrium. This is something that we have used a whole bunch. There's nothing new on this slide. All we're doing is giving it a name. And that's because a lot of the times these tension problems, they are often in translational equilibrium. But like I said, this is absolutely nothing new. We've been using this a whole bunch already. And so translational equilibrium is just when the sum of all the forces acting on an object is equal to 0. In other words, the net force acting on an object is equal to 0. Okay, and then because we know that motion is independent in the x and y directions, this tells us that the net force in the x direction is 0. In other words, the sum of all the forces or components of forces in the x direction must be equal to 0. And similarly, the net force in the y direction, which is the sum of all the y components of the forces acting on an object, must also be equal to 0. Okay, and so whenever you have a translational equilibrium problem, you're going to be told something like the object is at rest, or the object has constant velocity, right? Because then you have no acceleration. Velocity isn't changing, so acceleration is going to be 0, and that tells us that the net force is also going to be 0. Okay, and so you'll be looking for words like at rest, balance, constant velocity, something like that. Okay, so just one example here. This is something that, we've done a few times at this point. So here I have a box. There's a normal force upwards, weight is pulling downwards. Here I've used a frictional force, which is opposing motion because I have some applied force that is downwards and to the right. And so what I could do is if this box is moving with constant velocity, then I would say, okay, immediately the net force of this acting on this box must be 0 in the x direction, and it also must be 0 in the y direction, right? Because the acceleration in the x direction is 0, and so is the acceleration in the y direction. And so then I can just sum up the forces acting on the box in the x direction. There's an x component to this applied force going in the positive x direction, and then frictions in the negative x direction. We could sum those together and set it equal to 0 to solve for some unknowns. Similarly, we know that the net force in the y direction must be 0. The applied force has some component in the minus y direction. We know that weight is also in the minus y direction, so that's mg. And then the normal force is pointing upwards. And so minus the y component of the applied force minus the weight plus the normal force must be 0. So you'll have situations like this that crop up quite a bit, and we'll be doing some examples in class. Okay, so also when we talk about tension, and when we have ropes or strings in our problems, a lot of the times we have connected objects. So when we have connected objects, it's similar to, remember when we did the contact forces and we had objects that were like pushing up on each other? It's the same sort of idea when we have objects connected by a string, that the objects are accelerating at the same rate. So you can think about the overall acceleration of the entire system. So what we can do when we have boxes or objects that are connected by a string is we just remember that they have the same acceleration. When we have things connected by a string, it can be a little bit trickier than when we have just the boxes that are in contact with each other, because the strings can go over pulleys and stuff, and so they can change directions, so the forces can change directions, and so it gets a little bit trickier, but it's the same general concept. So what do we want to do to solve problems when we have connected objects? First thing I always do is draw a free body diagram for each object. So here I have two boxes, they're connected by a string. I want to know what is the tension in this string. My first box has mass m1 and the second box has mass m2. They're moving with some velocity to the right, and there's an applied force also acting, pulling on box 2 to the right. Okay, so first thing I did here is I drew a free body diagram. If you look at box 1, there's only one force acting on it, and that's the tension in the string. If you look at box 2, the tension in the string is pulling it to the left, and the applied force is pulling it to the right. So these would be my free body diagrams, ignoring gravity and the normal force in this case, since I'm interested in motion in the x direction. Okay, so that's going to be my free body diagram. Next thing you want to do is find the net force in the x or y direction for each object. And so here, if we think about the net force on each object, for object 1, there's only one force acting, and it's in the positive x direction. So I would say that F net x for object 1, I know, it gets terrible, all these little subscripts. So the net force in the x direction for object 1 is just equal to the tension. That must also, by Newton's second law, be equal to the mass of object 1 times the acceleration of object 1. And so this is going to be the net acceleration in the x direction of both object 1 and object 2, right? Because we said they're moving together, so they must have the same net acceleration. Okay, and so then I can solve for the net acceleration in the x direction. This will be the same for object 1 as object 2. It's just going to be equal to t divided by m1. Okay, then we can look at box 2 here. So box 2 has a net force acting on it in the x direction. That's going to be equal to minus the tension, since the tension is pulling left, plus the applied force, since the applied force is pulling to the right. Then we set that sum of forces equal to Newton's second law, which tells us that this has to be equal to m2 times the acceleration of box 2 in the x direction. Again, this acceleration is the same as object 1 since they're connected and they're moving together, and so it's just going to be a net x. Okay, and so then I can go ahead and solve again for a net x. Here I'm just going to divide both sides of this equation by m2, and I get a net x is equal to minus t plus f applied divided by m2. Okay, so that was pretty straightforward in this problem. We didn't have any pulleys. When you have pulleys, things get a little crazy because it's the acceleration along the direction of the string that remains constant for both objects. And so when you have a pulley, what's convenient is to take and define your coordinate system for one object. And then as the string, you follow the string with that coordinate system. And so as the string goes over a pulley, you kind of just tilt your coordinate system with the string. And so don't worry, we're going to do an example of that, but that will help you because it's really the acceleration in a given direction along the string that remains constant for both objects. Okay, like I said, we're going to do some examples, and so then hopefully that will make sense if that sounds a little crazy right now. All right, and so then after we have solved for our net acceleration for both boxes here, we just recognize that those accelerations are the same. And so we can set these two accelerations equal to each other to solve for our unknown, which in this case is the tension in the string. Okay, and so basically here the algebra gets a little ugly, but all I did was I set this bottom equation equal to this top equation here. And so then I just had to solve for t. It's on both sides, which is why it gets kind of ugly. But what you can do after a bit of algebra is find that the tension in the string is just the applied force divided by m2 multiplied by m1 m2 over m1 plus m2. So this is a little bit ugly. It's nicer if you have numbers, right? Because then you can just combine stuff instead of leaving it in terms of individual masses. But I just wanted to show you a quick example of how you can deal with tension in connected objects. Okay, so now it's time to do another example on your own this time. So we have a block with mass m1. It's on a frictionless tabletop and it's connected to a string that goes over a pulley to block with mass m2. So here they're released from rest and then they're allowed to move freely. And so we want to know, is the magnitude of the net acceleration of the entire system, do you think it's going to be greater than g, less than g, or equal to g? Where remember, g is the acceleration due to gravity. Okay, so let's see how I went about solving this problem. So here, the first thing I would do is just draw a free body diagram. And specifically, I'm going to draw a free body diagram for mass 2. So when I look at mass 2, I know that there are two forces acting on it. It has its weight pulling downward, which is just going to be m2 times g. And then there's going to be the force of tension pulling upwards, right? And so this is really like the force of mass 1 pulling on block 2. Right? And that's the tension pulling upwards in the string. Okay, and so then I'm going to go ahead and think about my coordinate system. So traditionally, I would define the coordinate system so that y is up and x is to the right. And so if you define that to be your coordinate system for block 1, then what you know is as you go around the little pulley here, this is where things get a little dicey. But so as you go around the pulley, you'll want to tilt your coordinate system with you. So you can see how I took this x and dragged it around, and so now positive x is going to be going downward. I took the y direction, which was up, and I dragged it around, so now the positive y direction is going to the right. And why did I do that? Well, it's because it's really the acceleration of block mass 1 in the x direction that's equal to the acceleration of block mass 2 in the downwards direction. So we want to make sure that those two things are both called the x direction so that we make sure that we're equating the accelerations in like coordinate systems. Okay. So with this coordinate system then, I can think about the net acceleration in the x direction by thinking about the net force acting on block 2 in the x direction. So that's just going to be the sum of the two forces acting. Because I've defined positive x to be downward, it's going to be m2g minus t. So t is upwards, it's going to be in the negative x direction. Okay, and then we set that equal to mass 2 times the net acceleration in the x direction, with the positive x direction being downward. Okay, and so then what you can do is you can solve for the net acceleration in the x direction. Here you just divide both sides of the equation by m2 and you get g minus tension divided by m2. So since you have g minus some number, it's obviously going to be less than g, right? A net is going to be less than g. And so I would say then that the answer should be B here. Okay, let's look at one more question then. So same setup, and now we just want to know, is the tension in the string greater than the weight of block 2, less than the weight of block 2, or equal to the weight of block 2? Okay, so really this is just a continuation of the last problem. So we still have our coordinate system that we tilt as we go over the pulley. And so then I can still think about the net force acting on block 2 in the x direction, which we just said was equal to mass times the net acceleration in the x direction. And it's also then equal to the weight of block 2 minus the tension in the string. Okay, and so since we know that the blocks would accelerate downwards, right? So if you think about physically what would happen if you release these blocks from rest, the block M1 would slide across the table and block M2 would fall downwards towards the ground, right? And so A net in the x direction is going to be downwards, which is positive. So just solving this equation, our Newton's law equation for the tension, we get the tension is equal to the weight of the second block minus mass of the second block times the net acceleration, right? And so since we said acceleration is positive, it's downward, this tells me that the tension must be something less than the weight of the second block. So that's the mathematical way to think about it. There's also another more intuitive way to think about it. So remember, the tension is pulling up on the block and weight is pulling down on the block. So if the tension is bigger than the weight, then the block would move upwards when you released it from rest, right? And we know, physically, that's not what would happen, right? So physically, we know that the block would fall downward. If those two things were equal, if the tension was equal to the weight, the block just wouldn't move. And so the only option that makes sense is for the tension to be less than the weight of the block so that the block still slides downward. Okay, so now it's time for our last topic today, which is circular motion with constant speed. So before we get started on thinking about circular motion with constant speed, we have to ask ourselves if we have an object that's on a circular track. So for example, a ball rolling around a circular track, and it's rolling around with constant speed. Is there a net force acting on that ball? Okay, so hopefully you thought that the answer here would be yes, there is a net force acting on the ball. And it's a little bit tricky, right? Because there's constant speed. And so then you might think, well, then there's no acceleration. But remember, the direction is changing as the ball rolls around the track, right? So as the ball is rolling, its direction is constantly changing, which means that even though the speed is constant, the velocity is changing, and so there will be a net acceleration, right, that causes that change in velocity. And when we have net acceleration, we know from Newton's second law that we must have a net force acting on the object. So yes, there should be a net force acting on the ball as it rolls around the track, even though it has constant speed, because its velocity is not going to be constant. Okay, so let's think a little bit about this force that acts on an object that's rolling around on a circular track with constant speed. Okay, so we just said that there must be a force acting on it, and it turns out that that force must be pulling the object towards the center all the time. So the way I would think about this is, imagine you have like a ball on a rope and you're swinging it around your head or something like that in a circular path. So if you think about it, as you're swinging that ball around on that circular path on that rope, if you were to release the rope, the ball would go flying outward, right? And so your hand is really pulling it towards the center all the time as it goes around that track. And that's what keeps it on that circular path. And so really there's going to be a force that's pulling on the object towards the center all the time to keep it on that circular track. And we call this the centripetal force. Centripetal is Latin for center seeking, and we use the symbol little f and then Cp. So little f Cp for any force that's directed towards the center of a circle. Okay, so here I have a ball that's rolling around the green track on a circle. It has constant speed as it rolls around, but you can tell that the velocity is changing at each different point on the track, right? So it's different at point A, then B, then C, because it's pointing in different directions, even though the magnitude would be the same. And so then at each point, the force acting on the ball would be directed towards the center of the circle. And so FA is going to be like in the negative x direction, FB would be downwards, and FC is kind of at this angle, right? But it's always just pointing, it's acting on the ball, pulling it towards the center of the circle. All right, and then because we know we have Newton's second law, so if there's a net force acting, then there must be a net acceleration as well. And so we can calculate the net acceleration. We refer to it as the centripetal acceleration. It gets the symbol ACP, and this is just the acceleration of any object moving in a circle. And then we know from Newton's second law that FCP must just be equal to the mass of the object multiplied by its centripetal acceleration. And so the centripetal acceleration is also always directed inwards, right? Because mass is always positive, and so we have the vector centripetal force multiplied by the scalar mass, and so A and F are always going to be in the same direction. And so that tells me that the centripetal acceleration will also point inwards towards the center of the circle everywhere on the path. Okay. And so then what can we find out about the centripetal acceleration? Well, so it turns out that when you have an object moving on a circular path with constant speed, so let's say that the constant speed is v here, then it turns out that if your path has a radius little r, the centripetal acceleration is going to be v squared divided by r, and it's always acting towards the center of the circle. Okay, so let's do a little verification first, showing that the centripetal acceleration does point towards the center of the circle. So remember that the acceleration is just change in velocity over change in time. So I've chosen 2 points on the circle. I've called them A and B, and the velocity at point A is pointing up. The velocity at point B is pointing upwards and a little bit to the left. So if I wanted to figure out the acceleration, I would need to think about the change in velocity over the time frame that it takes the ball to move from point A to point B, and then the acceleration would be directed hopefully towards the center of the circle. So let's verify that that's the case. Remember, change in velocity is going to be VB minus VA. So I have VB pointing upwards and to the left. minus VA would point down, right, since VA points up. And so we can do some vector addition here. We place the tail of minus VA at the tip of VB, and then when you connect them, you get delta V. And so delta V here, it's pointing downward a little bit and inward. And so if you think about placing that vector over here on the path between VA and VB, it would in fact point towards the center of the circle. Okay, so that's what we expected. Now for the hard part. So now we want to derive the fact that the centripetal acceleration is equal to v squared over r. Don't worry if you don't follow all of this. You will not be required to derive this equation. You're just going to get to use it. But I wanted to show you where this came from. Okay, so first of all, to find the magnitude, we have to find two things. We have to find the magnitude of the change in velocity between those two locations. So here we're going to say between locations A and B. And then we have to find the change in time between those two locations. So how long does it take the ball to travel from point A to point B? And that's just because, remember, acceleration is change in velocity over change in time. So that's our goal. We're going to start by looking for the change in time. So how long does it take the ball to travel from point A to point B? Okay, so to do this, we just remember that speed is equal to distance divided by time. So we know the speed along this path is going to be a constant. We said it was a constant value v here. And so if we can figure out the distance of the path between those 2 points, then we could figure out the time it takes to travel between those 2 points. So it turns out that the distance between those 2 points is well approximated by something we refer to as the arc length. And so the arc length is basically like the fraction of the entire circle that's swept out by this angle phi here between points A and B. So if you think about it, the entire circle has 2 pi radians. And so the tiny fraction of this circle would be like this angle phi divided by 2 pi. Okay, and so then it turns out that we can multiply that by the entire circumference of the circle, which is 2 pi r, to find the length of this little arc. And so it's basically like the fraction of the entire circumference, which is 2 pi r. The fraction is going to be the angle phi divided by 2 pi. And so when you multiply that together, you end up getting r times phi. So that's the distance traveled here between points A and B. It's going to be the radius of the circle times the angle swept out between those 2 locations. Okay, so I plugged that in over here for the distance traveled during time t, and so then you end up with t equal to r phi divided by v. Okay, next up we want to find the magnitude of the change in velocity between points A and B. Okay, so we have to use the arc length again, and so now what we're going to do is use the fact that the angle between the 2 velocities is also going to be the same angle phi in here. And so then it turns out that the change in velocity, the magnitude of the change in velocity, is just going to be 2 pi times v, again then multiplied by that fraction of the circle that's swept out by the angle phi. And so it ends up being just v times phi. So v here was like the radius of our little circle for this arc length approximation. Okay, so don't worry too much if the arc length approximation confuses you. Like I said, that's not something you are required to know. Okay, but so then we have delta v and we also have t, and so then the centripetal acceleration is just going to be the magnitude of delta v divided by t. We found that the magnitude of delta v, remember, was just the speed times that angle phi, and then we divide by the time, which is just r phi divided by v. The phi's cancel out, and we're just left with v squared over r, as we expected. Okay, last point for today, the centripetal force is really any force directed towards the center of the circle. And so plugging in the fact that the centripetal acceleration we just found when we have constant speed, it's v squared over r. So then the centripetal force is going to be mv squared over r. And this is really not a new force. It's going to be one of the forces that we've already talked about acting. And so, for example, if you think about these kids playing tetherball, the tetherball is being pulled in towards the pole by the force of tension, really. So tension then is our centripetal force in that example. The satellite orbiting the Earth, it's always being pulled towards the Earth by gravity. So in this case, gravity is acting as our centripetal force. In your washing machine, the clothes are always being pushed towards the center of the washing machine due to the fact that they're sitting on that circular surface. And so really then it's the normal force that's acting like the centripetal force. And finally, cars on a track or a bicycle going around a tight turn. It's really the force of friction resisting the fact that you would alternatively slide out around that turn. It's friction pulling you in towards the center of that turn, and so friction acts as our centripetal force. Okay, that's it for today. We'll be doing lots of examples in class, and we'll actually be continuing with centripetal force next time. So I will see you in class.